test. So you have both dogs and cats at home.
By some reason, let me disable microphone. Hello, Anand. Oh, Anand is here. Yes, I see. It always, and Umar is here. Okay, now if I count attendees both online and in person, I get double number of attendees.
Okay.
Okay. I don't know why we have less people, because this meeting is much more important than previous one. If I would be in class, I would rush to come to this meeting at first. So those who the list of hello, Adam. Yeah, nice seeing you connected. Sharing screen. Sure. Okay, so here is the list of subjects that we are covering. So the last three presenters, Amara, Sarah, and Anand, are safe. I guarantee that their subjects will be covered no matter what. Those Rizvi, Wenjan, and Umar are also safe because we covered it before. And now the rest of the class, Haley, Adam, Lola, Hanman, Amir, Hadassah, and Payman are under the danger, because I will try my best to squeeze and demonstrate it as much as. No, Hadassah is safe too, because it was last time. Hello, Amir. Okay, yeah. So the last three things are very important for the projects. The projects that we will start soon will be formulated in the following way. How the properties of materials of your choice are being changed upon thermal excitation, upon thermal influence. And thermal influence means that all ions are experiencing thermal motion. Before today, we were dealing with the static. Hello, Sarah. Before today, we were dealing with static. No payment. Very happy to see you. Static molecules and materials at 0 Kelvin when ions were not moving. Today, I will start from covering these three things, which will show how to run molecular dynamics in VASP. Some of you were doing molecular dynamics in your previous life, in your out-of-class life for like force field molecular dynamics, which is great for big models, and it is great in everything except modeling chemical reactions, modeling breaking or forming new bonds. There is a reactive force field that tries to catch it, but it is not yet as developed as ab initio molecular dynamics. And in this subject, we do have three stages. First, all models that we do have with us are optimized, or maybe even they are not optimized. They have, each ion has only 3 Cartesian projections, right? So it is unambiguous position of an ion. But if we want to model realistic situation with ambient temperatures, each ion also has a velocity or momentum, right? Which should have another 3 Cartesian projections, velocity along x, y, and z. So we need to follow a procedure that will add these initial conditions for molecular dynamics, the momentum or velocities for each ion into the postcar. And after this initial condition is set up, we need to run actual molecular dynamics. So the section 1 in green, thermostat, it is a procedure for assigning velocities to each ion. When we do this procedure in our regular life in kitchen, it means we put a pot on a stove, like, right? We communicate some heat and all molecules start to move quicker. Or we put it on ice to slow it down. In experimental labs, there are several ways to control it, both in liquids and for solids, like baking programmable ovens that ramp temperature and do some thermal assisted processes. If you were following the emails, it was like instructions for LAB11 part 1. It was about summary of what we will do, all of us will do right now, and what Amara will present next week. The second part, when the velocities are set up, one needs to run molecular dynamics. Basically, each ion experiences Newton's equation of motion. So the forces are defined by curvature of potential energy surface, and then there are increments in space, and there are changes for momentum. And then there is a movie, there is a change of all positions over time. So the running the molecular dynamics when the initial conditions are set up is one of the simplest things. So Sarah is very lucky. She has the one of the simplest tasks in this presentation. And then when we do have file which contains snapshots of molecular dynamics, so coordinates of all ions at each point of time, like 100 or 1,000 snapshots, then this file of molecular dynamics snapshots must be converted into something that humans can analyze. So these files are too big, and they just need to be visualized. We need to convert it into movies. I suggest to use VMD, and I will demonstrate how to do it, but there are alternative software. One can do it with JMO, one can do it with OV2, and you can find something on your own, but I recommend VMD. This is not the easiest, because if you just do a blind installation of VMD, it will show the movie only on a screen. But to create video files, one needs to install additional toolbox, which is called VideoMac. And I'm not going to present how to do it. So it is a heavy load on shoulders of Anand. Just look into internet, look for presentations in previous years, consult with colleagues at different level. Those who use Mac, the Apple Mac, do not need VideoMac. Instead, or those who use Linux or Mac, there is a Linux utility image maker FF2MPEG or PPM2MPEG, which replaces VideoMac. But majority of us are using Windows, and there one needs to install VideoMac and then in the VMD to set up a path. So I hope within the first hour I will go over these 3 steps. We'll make a tour, making sure that everyone is comfortable, and then in the remaining hour we will go step by step for remaining parts. The question 11, which is selected by Hadassah, was recorded at the last 10 minutes of last lab, and more than half of the class have completed homeworks based on this recording. I will try to repeat it, but I need to give focus to things that haven't been presented before. Okay. No one selected periodic potentials and hybrid functionals. Well, I need to present it either today or maybe when we meet next time before we go to the your research projects, because some of you will decide to describe properties of periodic crystals. And for periodic crystals, this momentum and effective mass are needed. But just in case if someone is curious and we are short in time, this subject was consistently presented in the each previous years that I shared the recordings. Okay. Yes?
Sorry, what's the difference between Amara task and my task?
Difference or connection? Amara explains what is temperature ramping, what is thermostat. No, there are different computational procedures. There are different in-cars, there are different settings. So you are presenting microcanonical ensemble, constant energy. And Amara presents constant temperature. Thermodynamically, it is different procedures. So you will do microcanonical, energy is conserved. And Amara will do temperature is conserved. And those are not independent, they're connected. The one that you are doing is not possible without the one that Amara is doing.
So my task is heating the reactor.
Yes. No, you shouldn't, well, all of us will do heating in a few minutes, just practice patience. But in presentation, you can just refer to the presentation of Amara. Tell like, please take the concar created by Amara, and then it will work the following way. Clear? So we all work as a team. We're not like a standalone, and they're building one after each other. But
Amara will lead the system to 8,000, and I will start the system at 2,000.
right. Yeah, thanks for asking. Okay.
So I made a mess here. Should I reward the housekeeper or they will come?
They will come anyway. Okay. Just so that we all feel comfortable and understand what we are doing, here is the result of molecular dynamics part. Here it is, let me illustrate it in the GMO, which is pre-installed on the photon. So this will not create a standalone movie. It is only what is recorded from the screen. But you see, we take one of the simplest models we started with. Each ion is assigned velocity, and then they move over time. And then it runs over. The structure. In the VMD, there is the similar procedure which simultaneously creates the file that later can be uploaded to YouTube. So one selects directory, selects file name, selects that one needs to visualize trajectory, and depending on your settings, like I create FFmpeg, but you may do different. And then when you run it, just goes forward. And as a result, it creates a video file. So I'm just running a little bit ahead of a horse, just showing where are we going to. And what is interesting in VMD, well, in several pieces of software, this dynamic bond, it draws a line between atoms depending on the interatomic distance. So if the amplitude goes too far, it will interpret it as a broken chemical bond. Okay, stop here, start sharing there. So everyone is invited to log into Photon, and from Photon log into NERSC supercomputer. Please raise hands if it makes sense and you know how to do it. So NERSC is fine, right? Please, thank you. Raise hands if you are not sure what it is and how to log into NERSC. You need instructions, right? Okay. So right now in this window, I am on the Photon, and there is a little prompt. Bin advice NERSC. So the last line here, SSH-I, with this continuation will bring you to this NERSC supercomputer. Let me share it in the chat. Paste. Go. So if I type this command, here, paste, it gives the following line. So user at, there are several front nodes, and to get to the directory where I should work, there is also a prompt. More bin, oh, no, just more or. Copy, chat, paste. So I'm going to this directory, same as on the Photon. There the home directory for the user is doesn't have too much space. CD CHEM676 22. So just in case if you're not comfortable browsing this directories, here is the command. Okay, and here I'm looking for, yes. Okay, I see there are subdirectories basically for everyone. I'm going to the one myself, going to LAB11, and there I have already made some. What is? No. Let me pause recording and answer the question of Adam. Okay. So now I am on in my directory on NERSC, and I will do the same things I did before over again, so it will be a fair game. And maybe to show the clean picture, I will just use slightly different temperature. So make directory heat, let's say 2500 Kelvin. Going to this directory. The directory is empty. I do need the postcard from what I was doing on the previous lab. I think it was like new 2. So from the previous run, when we were doing density of states and spectra of the titanium hydroxide, I borrowed from myself the quantcar. Quantcar has the same format as a postcard. So right now in this directory, I have the postcard, which makes me ready to do something. In addition to postcard, I need other 4 files, key points here, potentials, postcard into here, and I will need in-car, but this in-car that tells what to do is very different. I do not want to borrow the old one. And then I also want to borrow the script for submission job. I can borrow it either from my previous directory, or I can borrow it from the little prompt. They should be the same. Copy here. Now I do have 4 files, and in order to run WASP, I am missing the most important file in car, which tells what to do. So just as a little illustration, I can look on the in car that we were using last time. More in car. And by the way, I'm trying to condense everything, but if you are curious about content, just try to go to online and type WASP manual or just WASP, and the authors of this code give like 500 pages manual with explaining each tiny keyword, how to operate it. So it's the instructions are free. And if you really want to become professional, you just learn and then get an idea how to modify each little thing. It's difference of WASP from Gaussian is that Gaussian is like automatic transmission, and WASP is like manual transmission. You control all things, and it's too many details to control. But here we are using pre-made templates of the in-car just to save time in the lab. So the one we were using here was used for either geometry optimization or single point, and we can see like this Inversion 1 and there were several other things. Here now we need a specific in-car specific list of requirements that will assign velocities to each atom. So if I type more in-car, so notice right now I will look on the in-car that is designed for assigning velocities for each ion, and it will be very different from what we saw before. So the first thing, which probably you don't care, but before we had Ibrion 2, here we have Ibrion 0. So it controls the algorithm, how the parameters are changed. There are a few other parameters, but one that we want to learn is the N block. And now I think we will do everything in time. We will complete molecular dynamics in within the remaining like half an hour. But instead of just blindly showing commands, I need to tell stories. So what happens to a pot on a stove if you look on it microscopically? So a molecule of a pot or atom in the this metal structure of a pot is touching the surface of the stove, and when the atoms of a stove perform some chaotic motion, they hit the atom of a stove and assign velocities, right? Change velocity. So basically, what we and it happens not at one point, but simultaneously at several points. So there is, so to say, kicks. The source of heat kicks the receiver of heat, and then the atoms that have been kicked continue to move, but after some time, immediately or after some delay, they get kicked again, right? So the algorithm for assigning velocities is made in the following way. All ions in our model are obtaining random kicks, random in a sense that we do not know, they use a random number generator, and the kicks are arranged in such a way so that communicated energy will be equal to temperature, but the direction of each individual velocity projection is random, right? If you perform this heat transfer event only one, it will be not sufficient because this energy will redistribute over the whole model and the temperature will be lower than the one that we want. Therefore, one needs several kicks. And this N block is a parameter of between kicks. Let's VI in car. I'm going to use. So number 4 is good, but if you do research, you may do a little increase it. Here is the temperature where we start. Where we start is amount of kinetic energy at the first kick and at the last kick. We can continuously ramp it if we fear to break the model, but I'm just putting the same. And the same, so it is temperature in Kelvin. NSW, it is how many ionic steps. It takes about 1 second of computational time for this small model. So if we put 300, it will take 5 minutes. If I'm uncomfortable, if I'm really in a rush, I can minimize and I can then do 100 or even 30, so to make this job quicker. If I would do it on a photon, I would do only 30 steps to speed it up. POTIM is a amount of time step in femtoseconds. So saving WQ, and then submitting the job as batch debug. And then here is the number of a job. I want to check SQS, grab the number of a job. So it is running, which means I was the first in our group to submit this debug. Right now, after all of us will start submitting it, the debug queue can hold only like 2 running and 5 in the queue. So, but if you set up all jobs quite quick, then all of us can get through. So while the job is running, while the job is running, it creates additional files. And here the file OZCar is increasing. I'm just showing the tail. This little thing that we see on the screen is illustration what we were speaking in the class. So 36 is number of, no, 38, number of ionic step. And inside there are electronic self-consistent cycles that we did yesterday, right? So one gets convergence of the difference between total energies. So it gets, as soon as it gets smaller than 10 to the minus 4, it gets to next ionic step. When we do geometry optimization, it gives number of step, and then F equals, and then amount of energy, F for free energy. If you do molecular dynamics with, then it shows temperature in Kelvin. And you see, it is not literally 2,500 that I requested. It is sometimes bigger, sometimes smaller. So this, a convergence of the kinetic energy or temperature of a system to the pre-made request is a criterion of completion of the thermalization process. So those of you who are planning to run non-adiabatic dynamics for your research projects in the future, it can be all of us, it could be none of us, it could be Lola, Haley, and Hadassah. Their research project, to my knowledge, will depend on non-adiabatic dynamics, which depends on molecular dynamics. So if the quality of the results may slightly depend on amount of time for heating. So you may care about this aspect. So 100 steps, it is done, right? And now I want to analyze whether this heating was enough. If I am careless, I can immediately go to molecular dynamics. But I want to just do a little care and analyze what is going on. So please try to repeat what I'm doing, okay? And I will try to make a little less visits just to save time. So after completion of this job, I do have the whole zoo of WASP files. If I will look inside outcar, I will notice that the list of orbitals is repeated 100 times. At each time step, there is a new electronic structure, right? I'm not going to look into the outcar because it looks like, you see, it is a little bigger than usual. So it's like almost 2 megabytes, which is a little too much for me, right? The OZCar is a little shorter, so it just makes reports at each electronic step, what is the total energy. And the file, yes, OZCar. So more OZCar, it is what we saw. Let me bring up an interesting feature. Okay, so it is subject of Amara, right? So it's your target audience now. So first time we have 2,500, and then suddenly it goes to 0. So it is a little surprise and question that we may want to discuss. So we want to hit the model to 2500, and it just computes that the temperature is 0, 0, 0 again, 0 again. So, and then at the step 5, it is 2500 again. So n block time steps, which we set up for, there are no kicks. So at step number 1, we have assignment of velocities. 4 steps later, at 5, we have another assignment of velocity. And then we see temperature is a little lower than assigned value, and it keeps being changed. It like drops. So the temperature is dropping because kinetic energy is being redistributed into potential energy, right? So I'll stop sharing for a second and just do a little drawing. So if you do have total energy, which is contributed as potential plus kinetic. Right? So if we are at the minimum, the energy is contributed only by potential. If we suddenly promote system to a certain temperature, we will have like so many kinetic energy above the potential. And it means I'm too close to the speaker. It means that the system will start moving aside. And as system moves aside, the proportion between kinetic and potential changes. So we are getting less kinetic and more potential, right? And if you move further, we get even less kinetic and less potential. And if you get to the starting point, there will be zero kinetic energy. Make sense? And we want to avoid it because there are multiple degrees of freedom. We can assign kinetic energy again and again and let system equilibrate. And then we will get average kinetic energy corresponding to a given temperature. So how to monitor this process? So I can extract this values of temperature out of the outcar by grep T equals outcar. Not outcar, OZCAR. So it creates this list of temperatures, and I can direct it to a file. Let me copy paste this little command into chat line. Copy, chat, paste. Now I can try to analyze it visually. So GNU pod, quick. GNU pod. I do not want to bother this graphical transmission, and therefore I will do very old-fashioned. So set term dump, which means pretend that we are in 1970s or 1990s when there are no graphical terminals, only text terminals. Not setter, but set term dump. And then I can plot file TT using here. First column is time, second column is text, third column is temperature. Using column number 3, with line, And now it shows this little image. But let's make it a little bigger. 100. Okay, now it is a little bigger. So what we see, x-axis is time, y-axis is temperature, right? And we see that we assign it to 2500 and it drops to 0 and stays 0 until 4. Then it goes back to 2500 and then it drops a little less. Then we assign it to 2500. Sometimes it can go higher. Then we assign it to 2500, it goes down. But this deviation from what we assign is getting smaller and smaller and smaller, and then it stabilizes near the temperatures that we do want. So if the computational procedure that we want is dramatically depending on level of this equilibration, one can decide whether we want to do short or longer thermal equilibration, whether we are happy with small and block, or we can make it longer. And this figure is a criterion of achieving a good temperature. Make sense? Okay, and if I want to do a little bit better graphics, I can just quickly manipulate it, like set x label time, set y label temperature, set term post with some font size, set out maybe heat PS, and then I do replot, which means now it plots the same information into the file. I think how to operate the plot was a subject of Anand at few times, a few meetings before. Okay, now I do exit. Let's minus T heat head. And there is this file. There is this file. So PS to PDF WR TT. And I do want to
Queen, don't switch off that button.
this file in the graphical
It
format,
get lost.
then
We lost
transfer
our
first
connection
to
because
photo
of
and
it.
then
That is
the rest
connected to
are
the modem. That's why. If,
CP.
Oh my God, I used many times.
no. Every time what happened when you did that, whatever simulation we are running sometimes stops.
So it's okay. So you have to restart again.
Yes.
So,
No, means all the system it is logged out. I need to log in once again.
oh, so it's take time or you
Yes,
lost your
yes.
data or not?
No, I did not lost the data, but the thing is I lost the connection for this one. Sorry.
Ah, oh really? I don't know.
So this file is here, and I can download it to local terminal and just enjoy watching it. Yes. Just do same as you did in the homework. You didn't do homework. Last homework, number 10. The one that was due today. Uh-huh. Okay. Okay, I'll do demonstration once again. Just a second. You need to do it on NERSC, not on the. Did you copy the debug the submission queue script. So here is the file, and here it is in the graphical form. Okay, so please try to go over the steps. I will try making visits, but help each other as much as possible. So just try going along the steps, and if you do not know how to do not wait for me. Just kick your neighbor and ask, like, do you know how to do? And it is a major benefit of sitting in the class compared to online. Sarah, did you got the script? Did you copy it? Okay. Okay, I think it is time to make a visit. Otherwise, some of us can be a little behind. Let me sit behind between you, so you guys. So I just show it once, and you will repeat after. Something is missing. No postcard. No code car. So the VASP is panicking because it doesn't know which model to work with. There are no atomic coordinates. So LAB11. One car here, was car. Okay, and now let's redo this batch debug. We need to rush because there are only there is before others submitting. Oh, it's in a queue line, but it's okay. It will be there soon. Group debug. Let's watch what is going on. So 2 are running. You are the third in the queue, so not so bad. So when they're done, you the next. So it was main question, right?
Actually, I need to first copy that titanium files.
Oh.
Have those files in my folder.
Because you were not here last time.
Yes.
To save time, we will copy them from my directory, but in the future, you need to transfer files between your Photon directory and nurse directory. Okay, it's doable, but it's a little discomfortable because one needs to type. Okay, so what?
Yeah, these are the files for Oleg 8.
Okay,
Yeah.
okay, let's LAB11. Okay, copy LAB10. pause. And now we need the and we also need the okay. So just 300 is very boring. It will be almost the output. It will be very small. Let's do it a little quicker. Okay, you're lucky there is less than 5 people in the queue. Correct. Okay. Yours running. And you can which. Okay. Your is not yet running, but you can see who else is using the debug queue. How many? So total 2 are running. One of them is your neighbor, and yours is here. So as soon 2 previous are done, you will start, and you will get the car. Now it will tell there is no such file, but as soon as it starts running, you will get it. Oh, my pleasure. Wow. You did it. So you can help others.
Yes.
Huh?
Yeah, I can.
Okay, that's great. Yeah, thank you guys for helping each other. Great. Sir, did it work? Okay, yeah, thank you. So you're done computing and you're just transferring file. Okay, yeah, thank you. Okay, let me talk to those who are online. So, Haley, would you like to share screen?
I cannot. I think I need permission.
I do not hear and do not see anything. Oh yes. Oh, sorry. Yes. Just a second. We'll do just quickly. Make co-host. Yes, you can go ahead, sharing screen, and I will just make others co-hosts. Make co-host. Yes. Oh, wow, great. Thank you. It works. Yeah, thank you. You can stop sharing. And everything else, only Adam and Hanmant and Haley are online only, right? So, Adam, would you like to share a screen? Okay. Do you know how to convert it into PDF?
No. Can you hear me?
Or should we do it quickly together? I do not hear you. I hope it is not because of, well, let me double
Hello?
check that.
Hello?
Oh, yes, excellent.
Oh,
Yeah.
okay.
Should we do it together?
Yes. I don't remember how.
Okay, so we may want set X label time. I'm just set Y label temperature in Kelvin. I can replot and see that it shows this time and now I can do set term post for postscript if I want big fonts.
Ah,
Yeah. And then set output for some name that I like. And then just report. And then quit. And then PS to PDF of the file.
okay.
You will be able to transfer it and look on it.
Yeah, thank you.
Okay, yeah, you can stop sharing then. Hanan, would you like to share screen?
I will transfer
Okay,
the
yes,
PDF.
you did this, and now you need to transfer it to Photon, right? Let's do it
Yes.
together. Request remote control. So we are going to your other directory and check. Would you please copy the path? Oh, no, yes, yeah, correct. Copy only the path. Okay, copy. Now let's go to the here and do SCP, everything that ends with PDF. And now please paste the path. Enter. Hit enter and then type the password. Okay, and now we can just identify reconnect SSH browser. Okay, it looks like your homework. And here is your lab 11. and here is your TT. Make sense?
Yes.
Okay, you can stop sharing. Okay, let's go to the next stage for doing molecular dynamics. Actually, so we are going from subject for Amara to subject for Sarah. So if I look onto the Hond car, this is my main, how to say, achievement. So before we used to have only 3 Cartesian coordinates, right? Now, in addition to coordinates, we have another list of as big as many atoms, and it has 3 projections of velocities. So the Hond car file is the main information that we pass on from Amara to Sarah. So I'm going to create new directory, make directory molecular dynamics to 500, and then I'm copying this Hond car, which has temperature, which has velocities, from here to this new directory, and I will immediately call it pos car. Yes. What do you mean fix atoms? Yes. Yes. Yes, absolutely. So if you change letter T to letter F, it will freeze certain degree of freedom. If you freeze all 3 projections, you will fix a given atom. It will work both for heating and for molecular dynamics. Yep. So then we do need key points, put car. And again, I am not copying the in car. I do copy this debug script, but I'm not copying the in car. And then I'm going to this directory, CD, and I want to copy the template, bin in car molecular dynamics into here and call it in car. So let's look what is inside, more in car. So it also has Ibrion 0, but you see S-mass has different value compared to the one that we used there. So it keeps summation of kinetic and potential energy constant, and they freely repartition, and there is no heating. The temperature that one is using here is not the temperature. It is different temperature than the one in the previous run. Before, initial and final temperature was referring to velocities of ions. Right now, with S mass -3, beginning and final temperature refers to electronic temperature, to parameter that modifies Fermi distribution. Occupation of HOMO and LUMO will be not discrete, but they will be a little, HOMO will be a little less than 2, LUMO will be a little more than 0 because of the thermal promotion. If you want absolutely reasonable and correct, the temperature here should be the same as in the assigned temperature, but this is a parameter that is will not affect results unless your model is a metal. So if it is insulator or semiconductor, these parameters are not as important. Okay, 1,000 steps is is a little too much, because if you will be doing it in the middle of the night alone, you can do more steps, but now let's do only 100 as an illustration. Also, if later on when we will be doing projects, we can switch from using debug queue to regular queue, which will sit in the waiting line a little longer, but you can run jobs like 24 hours long. And if your models are big, NERSC outperforms CCAST. Even if you previously were running WASP on CCAST, you can make comparison. It's like different order of magnitude in productivity. Okay. Escape WQ. Yes, please. Uh-huh. Uh-huh. This parameter, let's instead of telling from scratch, let's just go and read. So okay, this is the heating. It is the one that Amar is doing. So nose Hoover thermostat is the thing that we just completed.
So if I run the simulation using nose canonical, and I set the temperature at the end and the beginning the same, and I ran for a long time, and then I skip the first hundreds, like 300, 400 steps, and take the last steps and equilibrate and do my analysis. So this is how I've been doing it, and I also found some papers doing the same, but I'm confused. What is SMAS, the micro canonical? I don't see the I don't understand the difference.
Yeah, thank you. Thank you, Sarah. If you will create movies, and when doing molecular dynamics, we always should create movies to follow what is going on with our systems, right? Without movies, molecular dynamics doesn't make sense. And you will make everything identical except this SMAS 0 and -3. The one for microcanonical ensemble with -3 will show a continuous motion with continuous velocities. So if you do it for a single atom, it will just move on a line, right? If you do SMAS 0, it will perform Brownian motion. It will move and then randomly change the velocity. No, grand canonical is when you have exchange of number of atoms. It is with chemical potential. But if it's not position, it will be randomness in velocities. So it will be Brownian motion. And if you simulate like gas thermodynamically, it could be reasonable for some of the applications. But if you have a small molecule with chemical reaction, when you look for some parts of the molecular system coming closer or departing from each other, you do not want to do nose. You do first nose Hoover thermostat and then canonical, because you want continuity of your trajectory. So in some sense, when you do nose, it is composed of several short microcanonical trajectories, but at the end of each trajectory, you randomly change velocities and restart. And a lot of applications would suffer from this. Okay. So just try. try my the one that you will be telling to everyone. Yes. Okay, let's keep going because time is running out. Okay, so here is the template. We just changed it, and now I just submit the job. So we're doing same as batch, debug. And now it made, oh, okay, it did let me in because probably you guys have completed your jobs. Now I do SQS grab of this number. And it is running right away. So, so if I will be watching how the Aussie car is developing, I will see that the temperature doesn't perform such sharp fluctuations as before. So it is a little more continuous. So you see it changes like maybe by 10 degrees rather than by 1,000 to 100. The remaining numbers here correspond, like EK is kinetic energy. Later on there is a entropy contributions, and before there is a potential energy. So one can plot all of them and look how the repartition between kinetic and potential energy is going on. So it will be done very soon. And as it is done, I can repeat the same protocol as we did for heating, as Amara will be showing. And my main goal is to make a movie. So I just, while I'm waiting for the jobs to end, I just tell a few words what is going on. So the file out car contains basically all information about the run. And one can, the VMD software is able to read out car directly. So one of the options is just to wait until this job is done, and then you download. First, you upload the out car from NERSC to Photon, and then you download from out car from Photon to your local computer, and then open it with VMD. It is completely legitimate. But sometimes out car has much more information and it is more reasonable. But VMD is one of the very few pieces of software that is able to read out car. In order to be a little bit more universal, we may convert this large out car file into a file that contains only XYZ coordinates at each time step. And there is a standard toolbox which is created not by VASP designers but computational chemistry enthusiasts. And this toolbox for processing VASP output is available both on Photon and on NERSC. So in this toolbox, there is a utility, there is a procedure that converts out car into XYZ format. And this XYZ will be more universal. You can open it with basically any computational chemistry software. So I will just demonstrate this little piece of software. Okay, 100 steps, things are done. I'm skipping making the image of how temperature is going on, but it will be much more smooth. So US minus OT, we do have out car. And here, let me type module show VASP. So and let me type it into the command into the chat line so you all see it. Copy. Paste. And here is the path to this toolbox. On Photon, the path is much more simpler, but on Photon, no one updates it. It is maybe a little obsolete, and on NERSC, there is a team of paid professionals who are just watching that everything is up to date. If suddenly I go to on Photon, this set of toolbox is in the here, VTS tools. And there is about 100 codes. So we need x.2xyz. So it's available on Photon, but I prefer to use on the NERSC. So I'm just copy pasting this path. And then typing x.2xyz. So right after this command, I am getting the file named movie.xyz. Copy. So if I look, I do not want to look into inside out card because it is too big. But if I look inside the more movie XYZ, it shows like snapshots. It looks like XYZ files for this model, but it's several replicas. So 9 atoms, and then coordinates for all of them. And then again, 9 atoms, coordinates for all of them. 9 atoms, coordinates for all of them, right? So I do want to upload this file first to Photon and then to the local computer. To directory MD 250. Copy. SCP movie. Okay, I did transfer the file. I think all of us can do it. I just in case, I can copy it into the chat, but I'm not sure it is ever needed. And then on Photon, I can open the JMO. Together with this file. Copy, paste. Okay. So I do have 2 instances of JMO open, one for previous run for 2000 and this one for the new one for 2500. So let's compare if it will give any different dynamics. So here I click animate and just push the button run. This will not create a movie, it will just show how things are changing over time. So it's even this high temperature doesn't break the molecule, although for less rigid molecules, some pieces may have been already broken by this high temperature. So there is just a little movie. And if I need a publication, I can just do snapshots at different time steps, right? I can monitor interatomic distance and analyze it. But now I want to create a movie, and I'm going to do it on different on a different computer. So I will stop sharing here, start sharing there. Okay. MD250. XYZ, and I will call it movie. Okay, and now I want to open so delete old molecule and download the new one. So I did download the molecule. Right now it looks very ugly with this mesh wire lines. So I want to change it so it will be a little bit more visual. So the drawing method should be changed to dynamic bonds, which is better. And I can also create this little dumbbells by doing balls. Okay, spheres. And if I just pull the little tab, I see the whole dynamics, but I do want to create a movie. So for this, I am selecting in the main menu extensions, then going to visualization and select the movie maker. So in the movie maker, I need to select working directory, otherwise it will save it in some far directories. So just click, select where I want to save it. And I want to define the name of the file. So renderer, the snapshots are sufficiently good. If one wants better quality, one needs to install additional toolbox for higher quality movies. And then we need only trajectory. Other options will just rotate molecule and create nice movies without any meaning. So trajectory, I do not want to garbage my computer, so I will delete image files after movie is done. And format, this is something we do not have time to discuss. I will try to help by visiting, but on Apple Macintosh, one needs FFmpeg. On the Windows, one needs VideoMac. So I select FFmpeg because it is installed, and then I just click Make Movie. So it goes over several snapshots, and in the command line where I executed VMD, it shows the progress, how the images are converted into the movie. And if after this I'm looking into the directory, there is a file that I was requesting, so MD 2500K. So after that, the only thing is left is to upload this video to YouTube. So click upload video, select files, and so last created file MD 2500. So it is demonstration for CHEM676 LAB11. No, it is not made for kids. It is public. Copy link. And it should be done by now. So let me share this with everyone in the class, and then I'm going to make a tour along seats and make sure that everyone can generate video like this. When you're done generating this YouTube video, please email it to me. Okay? Just try your best. Okay. So in case video mark doesn't work at all, a little way to save the situation is just to launch your Zoom meeting room, share your own screen, and then record it on your Zoom as a screen capture. It's not the best, but yes. So I don't know if you guys are doing it, if the following, but if not, please listen. Each VASP job must be run in a separate directory because VASP uses the same generic names of the files, and if you do more than one jobs in one directory, they will override each other and you'll have a complete mess. So anytime you run VASP, create a new directory. Otherwise, you will be lost in your own data. Good. You see what I'm... Okay. Now we are copying the templates for jobs, and then the in-car for molecular dynamics. Slash in-car dash MD. But if you've forgotten, you can just type this, then hit tab, and it will show several for anything you may need for this course. Okay. Oh, it is waiting in the queue. But it's not long to wait. You are just the first after then. Hear what we talked with Amir?
Yeah, the first of it.
Okay, so we have a directory, right? So we copy concar, which is the main productive part of this of the first calculation. Concar key points and the script to run this stuff. Now we go to this new directory. By the way, I have forgotten to change temperature, so your job will be at 300 Kelvin, which is very boring. Okay. Yeah, well, there will be homework where you will do many of those later on. Right now, we just need a proof of concept. So one file is missing. There is no in-car, right? Copy bin in-car. And then there are several templates.
So what is this in-car? This is the in-car from the previous folder.
Just watch. So I'm typing tab, and it shows there are several in-cars, right? In-car for, and I'm looking for something related to molecular dynamics. MD. Period. In-car. So if I look more period in-car, the previous one that you just did.
Right.
So it has LAB11, SMS -1. Now here we will show the one that we got. So it's SMS -3. It's different, right? And we need to modify it. So we have this file. We may have a little shorter trajectory, and we may want to. This temperature changes nothing. The temperature, you're safe. Temperature is inherited from previous run. If you use concar for higher temperature, then molecular dynamics will be at the same temperature. No. It does read temperature from the concar, from the postcar that was former concar. So it reads velocities of each atoms and composes temperature out of them. Okay. So we can do something here, but it will not affect velocities. It will only affect electronic structure. And then yes, which debug. So it's PD means it's yet pending. You can see how many people are also using debug. 2, 3, 4, 5. And you are the first in line after those that are running will finish. So it will start quite soon. Not yet running, but one can tell the car. So as soon as your job will start, it will populate this with the car. And when it stops changing, you can Control C and do the rest of the steps. Yeah, thank you. Yeah, thank you. Wow. Looks good. Huh? The best way is to use VMD. If you fail with VMD, then you can open your own Zoom, like stop being connected, run your own Zoom in your personal meeting, record what is on the screen. Okay? No. It is, so try to open VMD. Huh? Yes, but there will be things that you will not see in the recording. Try to open VMD now. And open this, transfer this movie XYZ to your local computer and open it in VMD. And it is a primary task for Anand. You will teach all of us to do it next week. So you need to learn it right now. So what is your VMD? VMD, did you open it? Did you transfer movie.xyz to this computer? So now to this computer, right? No. So please do. Please download it. Okay, let's go to VMD. File open, new molecule, browse. Load. Click main panel. Look on the graphical. Yeah, see, it's very ugly. So this graphics representations. See drawing method lines. Change it to dynamic bonds. Click. Modify it a little thinner. Bond radius. Okay. Distance cut off increase to like maybe 2.1. Enough. No, yeah. Okay. Now create wrap. Dynamic bonds VDV van der Waals. Click. Sphere scale smaller until. Okay. Good. Now let's go to main menu. Yeah, here. Yeah, extensions, visualization, movie maker. Select working directory. Just click and select where you want to save. Desktop, okay, select folder. Now, movie settings, trajectory, name of the movie. Now try to make movie, but it will show you some errors. So see, it needs video mark. So you need to install it and then answer yes and show in which directory it is. Okay. If you did install video mark, then yes, and you need to learn what it is. Just find online what is video mark. No, those are snapshots as images. But in order to combine all images into one movie, you need a specialized software. Let's open a browser. Just open a browser for me, please. And type like in the Google video mark. Video mark H, like an H at the end. Enter. Okay, and you need to download and install and learn what it is. Okay. Bring the main. That's okay. It will change in a second. I run it on this computer. For some reason, it's very slow. It should be a little quicker. Are you running anything else on your computer? But yeah. But yeah. So the dynamic bonds is for drawing lines and VDV for drawing spheres. It's just two different procedures. Okay. Okay, yeah, I see. Okay, very good. Okay, did you download and open it with VMD? Okay. So I think for Mac, you need FF and tab. It is not as quick. It will take a longer time than we have right now. And if things do not work at all, you can just open your own Zoom room and just capture the screen. Okay, let's look over those who are online. So, Hanman, would you like to share a screen? Wow, really great. So please upload it to YouTube and send to me. Can you show your VMD panel? Okay, and how did you install VideoMac? Can you just tell a few words into enable microphone and just tell to all of us, because several of your colleagues are trying to do it.
For me, VideoMac is already installed. I asked a COTech person to install it on my desktop. So I did not do it by myself.
Oh, so you're the lucky one. You do it on a public computer where it is already installed.
Yes.
Okay. That's good. Okay, yeah, thank you for showing, and please email me the link to upload to YouTube and share the link, and you can stop sharing right now. Haley, would you like to share screen?
I have this video Mac, but I don't know what to put for the pathway for it.
Okay. So let's.
You can go to.
I'm not the best expert in the.
So once.
But
Can I take? Once you create a movie, it will ask for the path. That time, just go to the your C drive, and where in the C drive, go to your program files or programs. In that, you can see your software VideoMac, where it will have the exe file for it. So just click on it, so it will automatically create a movie for you.
Okay, let's follow the suggestion from Hanuman. Okay. So C.
Okay, where do I go?
Yes, C drive. Yes, in program files. Go below. Go back in program. Just go back.
Is it programs or programs x86?
Go program files. 86 maybe below. VideoMac. Double click on it. Go below. Go below. That VideoMac. Click on that. Open.
Well,
So you can start click on start, so it will create the movie.
Okay.
Now it should be there.
Now let's, if it is ready, you can try uploading it to YouTube.
It is which folder you are already in. So go to that folder.
So users.
Desktop on, I think it is desktop movie.
I don't see it.
I think it is on Windows desktop. So can you just check on that?
It should be the same, but I can check. I don't see it.
Let's scroll and see.
It's,
I
think it is the same. Just once again check the folder where you saved.
So see users.
Users are see. Just go to see.
Okay, it looks like it is there.
Oh.
Okay. Very
we
good.
did
Very
it.
good. Yeah, thank you, Hanmant. Great help. Yeah. So, Haley, please try to upload this file to YouTube and share the link. Adam, would you like to share screen?
My job has been running for ages now.
Probably you didn't change the number of NSW, so you're running it for 1,000 steps instead of 100.
Yeah.
Oh, thank you, Haley, for sharing the link to video Mac. No, Adam, I think you did change NSW to 30, so it should be done really quick. More Aussie car. Huh. Oh, probably you did submit the job first and then modify the in-car.
Oh, shoot.
Sometimes it happens. Okay, one can convert out car into movie without waiting for completion. So module show WASP. So we need this VTS script. Paste x dot to xyz. T. So you have this movie. SCP. Copy. Paste. And now let's navigate through Scratch 001. CHEM year 2002. LAB11. MD. Movie. Desktop. Okay. Now you need to open VMD. Okay. So click, browse, desktop, open, load. Yeah, it's long and interesting dynamics. Just let it download. It will be, let it go on its own until it goes to about 1,000. Okay, and now let's course display white. Graphics representations. Lines can be replaced with dynamic bonds. Dynamic bonds can be thinner and longer. Okay, tetrahedral. And in addition to bonds, we may want to create wrap and add VDV, which should be, radius of a sphere should be smaller. Okay, now you identified extensions, visualization, and movie maker. And their set working directory. For example, desktop, select folder, MD, and now settings, trajectory. So make movie, and you see it goes.
Thank you.
But it is not. You're not done yet.
Yeah.
When it goes to the last stage, it will give you like error message and will ask you where is your video mark.
Okay.
So if you haven't installed it yet, you should follow the link provided by Haley. So she did send it in the chat line. Or okay, you already there.
Okay.
Should we finish on this? What will we change? Okay, and now in the VMD, just open VMD and look as it went through. Let's look for other VMD panels. It may have asked for giving the. Okay, probably it was among the error messages. Maybe we need to rerun. like stop and try once again. Visualization, movie maker, trajectory. Okay. Once again. What's going on?
Assign a different directory.
Huh?
Assign a different directory for saving.
Okay.
Mm.
Yeah. Good. Test movie is okay.
It's frozen.
Hit enter.
Yeah, there we go. Okay.
Maybe let's restart the VMD.
Okay.
Maybe just try typing the file name. Will be quick. Well, yeah, you can close it. Wait until it loads everything. Now let's try once again extension. Okay. I think in previous run it was conflicting with already made image files, and it was trying to create them twice. So after we're done with Adam, I will whoever needs to go can leave, and I will just record, and I will sit here and just do exercise of showing all steps needed for next week presentations. So I will skip visits and just quickly do demonstration, and it will be on the recording. So if your time allows, sit and watch. If it does not, feel free to leave.
VMD closed.
So if it keeps closing, you can try to shrink the video file to a little bit shorter, and one can edit it in the simple editor in the open the file with, well,
Okay, it looks like it's finished. It looks like I have all the image files.
but it should create not images, but the movie file.
Ah. So this,
And your VMD didn't ask location of the video mark.
oh, okay.
So when you are opening the file and trying to create movie, it should ask the location of video mark. So Adam, please try to figure it out on your own, because I want to make a demonstration for others.
Okay, yeah, I will.
Okay. And I hope it will work, but if it does not, you know, the last resort is just to launch your own Zoom, record your screen while your movie is running.
Okay, thank you.
Okay, yeah. Stop sharing. So let's quickly look what we are missing. Share screen. Okay, anions and cations. I plan to finish everything before 8, just as a plan. And again, if your time doesn't allow, feel free to leave. We are doing this little sacrifice for the allowing more time for the projects. We can easily postpone this little exercise to next week, but then you have much less time for projects, which is not good. Okay, stop sharing here. Start sharing there. Make directory 9. Copy. I just go there. So copy the last web key points. Now I can copy the in-car as well, and the debug. I'm doing it on a photon, sorry. Fresh as I should. So make directory and 9. Copy. Last web. Conc car here in the postcar. And then all 3 input files. In-car, podcar, key points, and the tools to run the job. I can also copy old out car with understanding that it will be overridden. So grab number of electrons from the out car. So in this model, the neutral model has 32 electrons. If I want to create an ion, I need to increase number of electrons. So VI in car, and I just add a line. So this n elect equals 32 is neutral. And if I make it 34, it will be an ion. So I save the file, do sbash debug, and it will be instantaneously quick because I do just a single point. So it is done. Now I can more code car and find the place where it shows electronic structure. Where it shows the list of orbitals. So there are very interesting changes. So for this exercise, the primary client is Haley, right? So before our HOMO was 16. Now our HOMO is 17. We have 2 electrons more, so it's D anion. And the gap between former HOMO and former LUMA is still the same, about 3.5 electron volts. But now the gap is much smaller because we just injected 2 electrons into this model. So if one makes this analysis, one needs to copy paste this list of orbitals, make the file states, save this file, and then make density of states and explore how does it look. So this, maybe I will quickly do this exercise, but then I will skip for others. So WC states and grab number of points out car, grab number of electrons out car, grab Fermi out car, bin address those norm. So number of states 13. I will look from -10 to 0. Maybe I should use less. Fermi is -1.9. Alpha plus beta is -0.6. Bits 0.005. Magnitude 1. Number of atoms 9. Number of electrons. It should be 34. Gap 3. Put bin GNU Pro DOS 1 is to PDF. And just copy the file. So if we compare the density of states for neutral system and for anion, there is an additional feature. So former HOMO is getting populated, right? So it's if you see density of states with this feature, without looking on a molecule, you can recognize that it is an anion. So you can use computational chemistry to analyze chemical systems just based on electronic structure. So it is a reduction, right? Like injection of electron is reduction. One can do, okay, I'm going back. Now I'm make directory cation. Make directory cation. I'm just copying everything from here to there, going into the cation directory, VI in car. What? Oh no, I'm in the wrong place again. Okay, make directory cation. Copying, copy everything into there, going to the directory cation and modifying the in-car. So if 32 is neutral, 34 is anion, then 30 will be D-cation. Why I'm using changing number of electrons by 2? Because it is a singlet cation. Because it is a singlet spinless configuration, and it will be unsafe to change it, electrons by 1. Later, very soon, we will, like in 5 minutes, we will do odd number of electrons. Okay, now as batch I need to remove wave car, otherwise it will be an error because wave car has different number of electrons. As batch debug SQS grep velocities. It is already running. It's already on the iteration number 50, so it's about to finish in a few seconds. Writing wave functions, it means we are really, really close to completion. Okay, job is done in 45 seconds. So now I'm doing more out car. And again, scroll until the place where there is a list of orbitals. So we see that now we were trying to withdraw electrons from orbital 16, but the 16 and 15 are nearly degenerate and there is a partial population, but this an attempt to remove electrons substantially dropped Fermi energy to lower energies. So if I want to analyze it, I just copy this orbitals, create the states file, and paste this list of orbitals there. And then if I want to do density of states, I do the same command address those norm. 16 from, I need to go a little deeper from maybe minus 14 to 0, Fermi's minus 12.5, alpha minus 8, 1, 9, 33. I'm gonna put, those one. He has to be GF. Those P's and now just transfer so you have cation, I have density of states for cation. So you see it is there is some similarity, valence band, conduction band, but one has less feeling. So the two electrons are withdrawn from the top of the valence band. So if you see this feature in the density of states, you recognize that it is oxidized species. And it works with molecules and with solids, with anything. Okay, now I really appreciate those who elected to stay. It's not mandated. Now I'm going to focus on the subject that I believe is was elected by Adam. So I will still stay in the even number of electrons. So what would happen to the system if we photoexcited, if you promote electron from HOMO to LUMO? So we keep the same number of electrons, but we promote electrons from HOMO to LUMO. So this is subject of screen. Yeah, Adam, next. Modified electronic configuration, excitations. So stop sharing here, start sharing there. Share. So I'm making directory, clicking make directory excited. Copying everything from here to there. And looking on the templates of the in-cars. So I need a car RV. Okay. So if you are trying to become a really advanced professional in WASP and you're interested in this excited states, you may look for the keyword FERV, which stands for Fermi weight. So this was little record in association with this ISMIR2 tells that we are manually modifying the population of orbitals. Grab and bands out car. So number of bands is 64, meaning that the total number of orbitals is 64, and in the neutral molecule, which is not excited, we have 16 occupied orbitals. The total number of bands, which means orbitals, is 64. And in order to get total 64, we need, what will be 64 minus 16? Okay, thank you. So if I use this notation, it will be equivalent to running ground state calculation. It will show that there are 16 occupied orbitals and 48 unoccupied. So it will just run smoothly and reproduce ground state calculation. Let me put a little comment. Instead, I can run the same population pattern by typing 16 times 1 and then 48 times 0. I'm a little tired, but one can do it. Okay. But this notation, let me put a comment, will correspond with all occupied and then all unoccupied. If we want to model an excited state, we need to take last occupied and replace it by 0, and first unoccupied and replace it by 1. So we create population inversion. We manually promote electron. And the simplest way is to just promote from ground to excited. But one can promote from HOMO minus 10 to HOMO plus 10, or any excitation. Why we are doing it? So it goes a little beyond absorption. This modification of populations will change electronic structure, will change forces, and may potentially change the geometry of a molecule. So upon excitation, molecule can decompose, like explode, or can create new bonds. So it's photochemistry. So I'm going to use to encode it in this compact form. So Fermi weight, Fermi weight equals. So I want 15 orbitals occupied, then 1 orbital empty, total 16, then 1 orbital populated, total 17, and then 47 orbitals empty. Okay. And because I know that geometry may want to change, I'm giving a couple of steps of optimization. Escape WQ. And now I'm trying to batch debug. Yes, please. Oh, it is already done. Or it's only the first step is done. There will be a few more. So, because I'm not brave enough, if one does some doubtful things, the molecule, like if you, not only here, just in my experience, if I draw a molecule by hand without pre-optimization by force field, if a human error makes some atoms too close or too far, optimization with big protein may decompose molecule, may like make a unrealistic mimicking of an explosion. And to avoid it, one may make protein time step, the smaller the better. Then even if the forces are too big, the atoms will not move closer or away to a very big distance. So it is a safety measure to avoid decomposition of a molecule. If I really want to find a optimal geometry, I may do like several thousand steps of very small time step, or I can do 10 steps of protein equals 0.001, then 10 steps of protein 0.01, then 10.1, and then maybe 100 of 1. And it will prevent me from breaking my or cracking my model, and it will be best way to arrive to the optimal geometry. Make sense? Yeah, thanks for asking. Okay, 10 steps are done, and now I want to look on the outcar, but I do not want to look the whole outcar. Maybe tail minus n,000 outcar more. So I'm looking to the last segment of this file. And now here is what I see. And it is, I believe it is very beautiful. So you see, there is a population of inversion, right? And it is electronic structure of this system if we truly excite, if we not just explore ability of absorbed light, but if we really promote electrons from lower to higher state. Here it looks like the gap is increased. Maybe if we let it relax a little longer with more steps, the gap will try to decrease. But right now we're just looking proof of concept. So it's always a healthy thing to VI states, remove everything, insert new record, deal with last line, WQ, WC states, grab number of electrons, and grab number of ions, grab Fermi energy. We need only the last one from this list, and bin address those norm. Number of states 21, minimal energy, let's do from minus 14 to 0, Fermi energy minus 8.3, alpha plus beta minus 0.6, 0.005, magnitude 1, number of 9, number of 32, gaps 3. Those file is written GNU prot bin GNU s not p dos 1 yes to pdfwr dos ps. Now I will create make direct excited go there pwd, and now I will transfer the file. Copy scp everything that ends with pdf to the CHEM NGCU edu, paste. Okay, now excited those PDF. So you see, it illustrates that we did withdraw electrons from top of the valence band and promoted them to the bottom of the conduction band. So this is a critical skill to describe photochemistry, and one can do a lot of competitive research just on going this direction. Adam, do you have quick questions on the skills?
No, not right now.
So please try to repeat and teach others, because right now we all are not very fresh, and when it will be time for presenting, you will be our major teacher and instructor.
Okay.
Okay, yeah, thank you. So what is next? Okay, Will is not here, but I'll still show, because otherwise, oh, and we can skip Hanuman because it is what we were doing before. It is just density of states for singlet and what we were doing right now. So I'll show for all, and then it is for all and Amir. It is very similar things. So we have 20 minutes to finish everything. So stop here. Start sharing here. Okay. So make directory. I spin. Or maybe make directory singlet. Singlet. Neutral. Copy everything into sing. Oh. I need to do them on the same level. Okay. Copy everything into singlet neutral. CD singlet neutral. VI in car. Oh, I'm doing the same error. I'm on the photon instead of Norsk. Make directory singlet neutral. Copy everything into there. Go into this directory. VI in car. So right now we do not need cation. We can comment out this line, so it will bring number of electrons back to 30. And now I will do only one thing. I will type. So please help me telling what commercial names, which commercial name Apple company assign to their products, which letter is placed in front of each object. So like iWatch, iPhone, right? So VASP was written before Apple company started. And they use iSpin. By definition, iSpin equals 1, because we do not keep 2 spin components. But if you want to have spin equals 2, if you want to have alpha and beta components same as in unrestricted Hartree-Fock, in Gaussian, we put I spin equals 2, so no other changes. Q, just in case I remove wave car because it may inherit something that I do not need, and then just as batch debug. So SQS grep So right now we do not have time for all of us repeating it and making visits, but at least those who are presenting relevant subjects are encouraged to try it either here or at home, because whoever teaches the rest of the class next week is like, he will try to carry responsibility of teaching all of us on that. Just group. Yeah, okay, it is done. So right now I'm going to type to look onto outcar. And I'm going to see a little surprise, or maybe it's not surprise if we were running Gaussian together. So at the end, look here. So I see the list of orbitals, but instead of number 2, we have number 1. So in each orbital, we have 1 electron. So HOMO is the same, but it has 2 electrons. And then later, we have another list of electrons. And it is independent, right? So we have spin component 1 and spin component 2, which is same as alpha and beta. So I need to copy first one, copy VI states up, paste, and then I will more outcar, scroll to this second list for second spin component, spin component 2, and copy the things in the vicinity of the gap. So the I states down, I paste. Okay. Now I do need to convert it into density of states. So number of lines in states up, number of lines in states down. Okay, and now I need to run address those up. Just checking if the file, okay, it was created. And now I need to do the same for those down. Okay, after this exercise, we do have 2 lists for density of states, those up and those down. And there is a script that plots this density, both up and down density of states together. It goes up, down. Okay, let's look. There is a chance that I may have made some errors because of hectic. No, I didn't. So right now it looks absolutely symmetric, right? So we took two independent lists and they are absolutely symmetric. But this is a singlet. We are using so-called spin polarized DFT. It's analogous to unrestricted in Gaussian. And we have up and down alpha and beta are equivalent. But now we are going, or whatever, whoever stays and watches or whoever watches it on recording, to change spin multiplicity, change the amount of electrons in alpha and beta. So for this model, for this charge, I cannot access doublet. To make doublet, I need to add or remove one electron, right? But if I have even number of electrons, the next multiplicity is triplet, right? So I am going to prepare triplet and make directory triplet neutral. Triplet neutral. Copying everything from here to there. Going to this directory and modifying the in-car. So the parameter to modify the amount, this balance of amount of electrons in up and down moieties is n up down, n up down. So if I set n up down equals 0, it will correspond to singlet. If I set n up down equals to 1, it will correspond to doublet, 1 unpaired electron. And if I put n up down equals to 2, it will be a triplet, right? 2 unpaired electrons, which means I'm going to take 1 electron from beta and promote it to alpha. Escape WQ as batch debug. $45, $84. So it is running and it is going to be done soon. You see that this spin polarized DFT is a little bit longer than neutral. So because there are twice the number of orbitals. When we look onto the Aussie car, there is a new record, MAG equals to 0. So it is number of unpaired electrons and it is interpreted as magnetization. So very often this actually the designers of WASP software were using it to describe magnetic materials. So unpaired electrons are corresponding to magnetization and it is used in electronic paramagnetic resonance. Okay, So looking onto the outcar. And now we will see again two lists of orbital energies. So spin component 1, which is alpha, and we do see that 16, which was our HOMO, is fully occupied, and 17, which was LUMO, is occupied almost with full electron, right? And if you scroll down for beta, the HOMO is empty, and because it was transferred from beta to alpha. Now I need to do the same trick and copy paste the list of orbitals into VI spin up. I paste WQ. Copy VI, not spin, states down. I paste escape WQ and move, correcting my own error, spin up into states up. States up. WC states up. WC states down. Grep Fermi outcar. And now I'm repeating this bin dress those up. Number of states 22, energy from minus something to 0, Fermi minus 6.8, alpha plus beta minus 0.6, 1, 9, 32, 3, written. Same put down. Number of states 22, 0 and 6.8, 6.05, 1, 9 and 32, 3. And after this, I'm just rerunning this GNU plot, GNU proc spin up down. Those up down PS. And I want to watch this my directory neutral. Copy. SMP SMPDF. Okay, let's look how it. So we see if we intentionally create a triplet, it removes an electron from top of the valence band in beta and promotes it to the bottom of the conduction band in alpha. And because of this change of configuration, the mutual energies of alpha and beta are changed. So this is important if you study magnetic materials, radicals, and metal organic complexes. So this is a subject for Lola, and let's see. Lola and Amir. So you should do doublet yourself, but there you may take this octahedral, like titanium OH, titanium H2O6, 3+. Okay, light to matter interaction had assay. Yes. Spectra for singlet, doublet, triplet. Is it the only one thing left, right? Everyone else is done. Should we torture each other and sit here, or maybe I can record another video from home and then share with everyone, so that what is your vote? Go home and I make another video later, or everyone wants to stay here? So home or here? Oh, huh? Payment, you would like to go home now? Okay, yeah. We will, at least I will provide a personal instruction how you teach others. So basically, for the configurations that we just studied here, like triplets, there is a special list of commands that make spectra, because there is a contribution of spectra coming from alpha and from beta, and then one needs to merge them together. Okay, and I'll share. It is not long, but I think everyone is tired and we are already 1 hour longer. So many thanks for your patience. Send me requests if there are questions and if you need more material to prepare your talks. So the presentations is the top priority. I will distribute your votes, your talks over the Monday and Tuesday in the same way as it was before, because I know who can come on Monday, who can come on Tuesday, right? And then send it for your approval. There will be another homework due in a week from now, and basically I will ask you to practice some of the skills in application to longest oligomer chain. Maybe make movie of the oligomer 32 and compute triplet dose for oligomer 32. I will type it, but it will be basically this. Okay, thank you much. Meeting is done. Everyone is very welcome to depart and disconnect. Thank you for your patience. I'll stay here to answer any questions, but nothing is needed right now.
Thank you.
Thank you.